The Adelic Langlands program seeks to integrate the smooth geometry of quantum fields with the discrete, branching architecture of p-adic space. On one side, we have the real number line, extending seamlessly as a continuum. On the other, the totally disconnected p-adic network, which behaves like a fractal system, branching infinitely into discrete layers. Standard functional analysis attempts to contract these two models using a completed tensor product, forcing a real vector space to interact with an infinite product of p-adic spaces. Because their internal structures are incompatible, the output is a non-Hausdorff vector space. The matrix blurs into a chaotic, uncomputable state. This divergence shatters continuous functions. Determinants encounter infinities, causing eigenvalues to drift and breaking the rules of homological algebra. Without a stable tensor product, computing the high-energy spatial overlaps required to model the early universe leads to a total loss of mathematical convergence. Since the point-set model produces these divergent results, tracking global cosmic invariance requires a framework where real and p-adic scales are formally unified within a single tensor network. To resolve this, the condensed mathematics framework discards the idea of space as a collection of isolated points, replacing them with liquid vector spaces. Here, space is modeled as a functor, a sheaf. Instead of querying a coordinate point, the system evaluates how a field vector behaves when mapped across a specific profinite set. Space uses a profinite tree probe as its testing environment, a compact space branching exponentially to track sub-Planckian intersections. A field tracking information across these discrete branches yields a numerical trace at each leaf node, bypassing coordinate point pathologies entirely. This transition enables the solid tensor product, the point where continuous real scaling and discrete p-adic valuations intersect. By lifting both field types into condensed sheaves and testing them against the same profinite probe, their outer product merges without generating non-Hausdorff divergences. This derived contraction yields a stable trace norm, meaning the global partition function converges without the need for artificial regularization constants. The solid tensor product allows disparate number fields to coexist as a unified, path-connected tensor network. In this liquid architecture, computing primordial non-Gaussianity shifts from a modal approximation to a rigorous calculation in the harmonic domain. This three-point overlap is computed via a homological chain complex of boundary operators. The system requires exact topological closure, the nilpotency rule, where D1 composed with D2 equals 0. This exact condition eliminates boundary leakage, ensuring the calculation converges perfectly. However, physical stress can deform these operators, creating a structural chain break. If the nilpotency rule is violated, analytical power bleeds across the complex, introducing phase noise that destroys the accuracy of the non-Gaussianity template. To counter this, the framework utilizes an automated self-healing layer through a derived projection filter. The algorithm uses singular value decomposition to identify the exact left null space of the D2 boundary operator. It snaps the corrupted operator back onto this orthogonal complement. Boundary leakage is removed, and the nilpotency condition is restored. Enforcing these projective resolutions ensures the architecture remains stable against phase noise, preventing a structural collapse of the underlying spatial grid. At arc-minute scales, where L exceeds 1500, the continuous metric approximations of general relativity reach their limit. This is the regime of nonlinear structure formation. Matter collapses into virialized halos, generating intense local gravitational potentials and volatile velocity fields. These chaotic streams attempt to inject high-energy phase noise into the liquid calculation, threatening the convergence of the global partition function. The liquid framework responds with a derived T-structure truncation. This functor slices the complex at the nonlinear threshold, dampening the volatile high-energy waves into a stable, compact subcategory. This allows the framework to reinterpret baryonic feedback, like supernova shocks and black hole winds, as modular Hecke characters. When a supermassive black hole clears the gas from a galaxy core, it launches a massive thermal outflow that disrupts local matter density. In our liquid framework, this outflow is evaluated as a phase filter. It applies a modular character weight that shifts the Satake roots of the vacuum, reallocating information capacity to match the work performed by the wind. The framework translates the thermal pressure of these shocks into a character-weighted algebraic shift, integrating the nonlinear stress into the stable modular structure of the vacuum. These homological stabilization layers leave a distinct and measurable footprint in the large-scale architecture of our universe. The invariant Ray-Singer analytic torsion acts as a geometric regulator, clamping the background spacetime and preventing it from drifting under late-time nonlinear stress. We can see this in the visual topography of primordial non-Gaussianity. Inside a tetrahedral space, the three-point correlations form a series of nested, concentric phase shells. The Hecke shifts of baryonic feedback suppress the matter power spectrum at ultra-small scales, soften dark matter halos, and preventing the runaway central densities predicted by point-set models. This suppression creates a quantized, phase-locked staircase profile in high-resolution polarization maps, a direct marker of the underlying arithmetic grid. This synchronized orchestration between astrophysics and number theory provides empirical evidence for the condensed mathematical engine. Spacetime functions as a liquid-stabilized arithmetic circuit, where the exact homological laws of the Adelic Langlands program maintain a topologically secure geometry, from sub-Planckian scales to the largest galaxy clusters.